Hello, and welcome to another one of Ethan's engineering videos. Today we're going to be taking a look at Bernoulli's leaking tank, which is my way of saying we're going to take a tank without a lid, pour some fluid in it, put a lid on top, and then poke a hole in the bottom to allow the fluid to drain out. Now, because we're putting a lid on top, we're going to have to deal with the pressure inside of the container as the fluid level and the fluid volume decreases over time as the fluid drains out. Obviously, to start, we can't just throw any math up there because we have to know what we're looking for and what the situation we're describing actually looks like. So first, what are we looking for? Well, we want to model how the height and by proxy the volume changes in this tank over time as fluid drains out and as the pressure internally resists further flow. To get started, we're going to have to draw our situation, so let's just get right to it. So I'm going to start by drawing a cylindrical tank right here. It's going to go down, it's going to go down, it's going to have a bottom. The bottom is still a cylinder even though it doesn't look it, but don't worry about that, I'm just lazy. It's going to have some radius r that we don't need to worry about, but I'll write that there anyway. It's going to be some, the whole tanker as a whole, is going to be some height, capital H. And we're going to obviously, after we've poured the fluid in, we're going to start with some fluid level right here, which I'm going to call HI, because it's our initial height of our fluid all the way down. We're going to mark this as height is equal to 0, H is equal to 0. And of course, as our fluid level slowly decreases, we're going to be at just some arbitrary height. We're just going to call this height H, and that's going to be between obviously here and our 0 line right there. Just a little arrow line right there to indicate this is our height right here, H. I don't need to put that there. There we go. So this is our basic situation before we do anything, because obviously we have to poke a hole in it. So this right here, I'm going to make it extra thick right there. This is our hole at the bottom of our tank that our fluid is going to be flowing out of at some fluid rate Q. So this is our flow out of our tanker. This flow Q is also can be described by the velocity of the water leaving. So we're going to write V2 right here because this is going to be position 2. So I'll just put a little 2 in a circle right here. And I don't know, I guess at our height level or whatever on the surface of our water, that's going to be location 1. So we're obviously going to be looking at, when we deal with our pressure, the difference in pressure between points 2 and point 1. But first there's a couple other small little things we need to take care of describing this. So we're going to assume the pressure outside remains constant even as the world goes on. So we're just going to put down here P2 / P external because the external environmental pressure is exactly the same as the pressure in the environment. It's just semantics, whichever one I want to use at the time. I'll mostly try to stick with P2, but I might use P external verbally, so this is just to remind you of that. And obviously we have a pressure on the inside of our tank, P1. Now, just like we have our initial height, and then as the fluid drains, our height changes, because the changing of the height changes the volume of our air, our pressure inside our tank is going to change as well over time. But because the way I described the situation was it was a tank without a lid, we poured our fluid in, then put the lid on top, we know what our starting pressure on the inside is going to be. It's going to match our external atmospheric pressure. So I'm going to write PI for our initial pressure is going to be equal to P external. So when we start at HI, our pressure I is going to be equal to the pressure of the external environment. Other things we need to talk about? Yes, so obviously as the fluid level changes, there's going to be some velocity of our fluid, so we're just going to call that V1, just for semantics to match our V2. We've talked about our flow rate, we've talked about our pressures, and I'm pretty sure, oh yes, as our pressure changes, we're going to assume the walls of our tank are very thick. And the reason we're assuming they're thick is because obviously pressure is going to exert a force on the walls of our tank and theoretically could bend or inflate, bend inwards or outwards the walls of our tank, therefore changing the cylindrical shape and therefore the volume of the tank. But we're going to assume that doesn't happen, and so because of that, the area of our circles are going to be constant. So the area of our tank, I'm going to call A cyl for the cylinder, and the area of our hole right here is also going to be constant. So I'm going to call that A hole. Don't think about that too hard. A hole describes the area of the hole that we're poking in the bottom of our tank. And now with this, I believe we have described everything we need to get into the actual math and derivation portion. So, as I said earlier, what are we looking for? We're looking for the change in height over time of our fluid level right here. Do this, of our fluid. Now, how can we model this in a way that makes sense? Because we can't just solve for it outright. We're going to have to use differential equations, because eventually after we do this chalkboard section, we're going to snap right into Python and code it up and use solve IVP to solve our differential equation for a function of h over time. But how do we get that differential equation? Well, the differential equation itself is really only 3 terms, and it's very simple. So we'll do that first, and then you'll see why it's not really 3 terms. It's a bit more complicated. But again, that's why we have the rest of this chalkboard for that. So earlier you realize I described the water coming out, not water, the fluid coming out of our tank with both Q, the flow rate, and at some velocity V2. And that's because the definition of flow rate is, the amount of water leaving. So we can define flow, Q, as being equal to a velocity of fluid leaving through a certain area. If you were to take a pipe, cut a certain cross-section off and figure out how fast the water was moving through that area at some velocity through some area, obviously the units here are meters per second and the units here are meters squared. Multiply them together, you get meters cubed per second, which is a volumetric flow rate. So this is just the definition of flow. Now what we can do is specifically apply it to our situation here. So the first thing that's really easy to do is say, well, what's the velocity we're looking at? Well, we care about V2 because that's the velocity of the fluid leaving our tank. And then what's the area we care about? Well, because this is moving through the hole, the area is just going to be a hole. So that's kind of that specificity part of this taken care of. Now we have to talk about Q. How do we get Q? Because again, I said earlier we were looking for the change in height over time. So great flow rate. It's not constant because it's going to change depending on our over time. So how do we relate Q to h, our height? And that's basically because, as I said earlier, this is meters cubed per second. This is a volume of water leaving our tank over time, which means that our flow represents a change in volume over time, specifically a negative one, because our flow is 10 cubic meters of fluid per second, but that's 10 cubic meters of fluid leaving our tank per second. So Q is exactly the same as a change in volume, and I'm going to use a kind of a Romany looking V just to make sure I'm clear here, because there's also a V here for velocity. I'll make him a little shorter. A negative change in volume over time. So now we can again apply our situation a bit more specifically to this, the change in velocity over time being negative, and rewrite this in our final form before doing a little shuffling in algebra. So because we're looking at a cylinder and there's a radial symmetry in our cylindrical tank, the volume doesn't just change over time, the volume changes not relative to its area, because its area is constant. And since volume can be of a cylinder can be described as the area of the circle that makes up that cylinder times the height, we can actually rewrite this as negative area of our cylinder, the cylindrical top, times a change in height over time. And that's still going to be equal to the velocity of water leaving multiplied by the area of our tank hole. So now we're looking at this, we see, okay, great, we have we have the change in height over time here, and we have a bunch of things that we know. So we can just rewrite this as the change in height over a change in time is going to be equal to a hole over, I'll put the negative up top, a hole over a cyl times V2. So, put a circle around that. We've got our differential equation that describes height over time. Plug that into Python, we're ready to go. See you later. No, I'm just kidding. Of course, the area of our hole is constant, and the area of our cylinder is constant, but we don't know what the velocity is of the water leaving our tank, specifically because just as our pressure changes over time and our height changes over time, our volume changes over time, our velocity changes over time as well, as a result of those changing heights and volumes and pressures and all of that. So we're not done quite yet because we need to know what V2 is. So how do we figure out what the velocity of water leaving our tank is? Well, we can do that using Bernoulli's equation. That's when our big man Bernoulli comes into play. So what exactly is Bernoulli's equation, and how can we use it here? Well, it describes changes in fluid situations. And I can just write that up here really quickly. We've derived this previously in class, and it's kind of fundamental chemical engineering knowledge, so I'll just write it up here. The change in pressure, so P2 minus P1 over rho, which is the density of our fluid. Again, we're assuming that the density of our fluid remains constant even as pressure changes. That's just one of our assumptions. And we're going to add the change in velocity, so that's V2 squared minus V1 squared over 2, plus any changing in altitude, which would contribute energy, G. We're going to assume G is positive, is Z2 minus Z1. And all that's going to be equal to negative frictional heating. So again, any discrepancy in this should be accounted for by frictional heating. But now this is the part where we do all of our assumptions to kind of make the math a little bit easier and less complicated and able to be done by a college student on a whiteboard and not some super famous mathematician who invented this equation. The first thing we're going to do is pretty easy. We're going to just completely ignore frictional heating. We're just going to set this thing equal to 0, put a big slash through it. We're going to ignore that. The other thing we're going to ignore, I wrote P2 minus P2 here, that should be P1, I don't know why. The next thing we're going to do is we're going to talk about V1. So because this hole is going to be pretty small relative to the size of our tank, and the flow rate out is going to be decreasing over time, and obviously the flow rate's not going to be very big, and the velocity of the water leaving is not going to be very big. The velocity, that change in volume distributed over the entire circumference or area of our tank is going to be incredibly small. This V1 is going to be very small. So we're going to approximate it as 0. And we're just going to cross this guy out. We're going to say he's equal to 0 as well. We're just not going to worry about the velocity of our of our water level decreasing. We're just going to write that out of the way. And then the final thing we're going to do is we're going to take a look at our altitude measurement here. And so if you remember, we defined our H0 as being the base of our tank, which I guess you could consider to be Z2, because this is our final location right here. I said this is 2. So whatever height we're at, because we're working at some arbitrary height as our fluid level decreases, H is going to be our Z1. So this is some 0.1, because again, this 0.1 is changing as our fluid level increases and decreases. So this whole term right here is actually approximated, not approximated, but by definition is negative H. So that's everything we have written down right here. So we could just kind of rewrite this and make it a bit neater. So I'll take care of that real quick. So P2 minus P1 over rho plus V2 squared over 2. That's going to be minus GH is equal to 0, right? So what we're going to do now is, well, we're going to look at what we do know and what we don't know. So we see H here, obviously, we want to get that on one side. And we see P1, which we don't know. P2, which is a constant, and V2. So V2 is what we're looking for, and we're kind of excited because we can get it in terms of H, which is what we want, considering this is a differential equation of change in height over time. So getting height on one side and V2 on the other, since that's what we're looking for, is good. So we're just going to move GH and this over to the other side. So we have, and then I'm going to also multiply by 2 and take the square root, just because that's a single step, but I'll do them separately just for show. So we're going to have V2, that's probably not big enough to see on our screen, so I'll rewrite it a little larger. We've got plenty of space. V2 squared over 2 is going to be equal to, when we move this over, it's going to be positive GH. And then we move this over, so subtracting it is essentially just going to flip that top of the fraction, because it's basically positive P2 over rho minus P1 over rho. So by negating both of those, we're going to get still a positive fraction, or like the positive term as a whole, but it's going to be P1 minus P2. Excuse me, I think I got some chalk dust in my throat. It's very irritating. So now we're just going to multiply by 2 and take the square root. And as I said before, then we'll be done, because we'll have found V2. So we'll do this. We'll do V2 is equal to 2GH plus 2P1 minus P2 over rho. And then just put this whole thing in a square root, and we're done, right? This is our V2. We found our V2, and we're all good, right? Like, now we're done. I faked you out here before, but now that we found V2, look, even in terms of H, we're good now, right? And unfortunately, we're not. Because, as we said earlier, just like with V2 changing as a result of the situation, evolving over time, so too does our pressure 1 change over time. So we aren't done. We still have to figure out what P1 is. So now, how do we figure out what P1 is? Well, that's actually a lot simpler than it seems, and it has to do with a very basic equality. And that has to do with our atmosphere, because P1 represents the pressure of the air that's trapped when we put the lid of our cylinder on. So as I said, again, just restating to make sure we're very clear and specific, we had an open top tanker, we poured our fluid in, then we put our lid on, and then we poked a hole. And out of this hole is only flowing the fluid, because the fluid settles to the bottom beneath the gas, obviously because gas floats and fluid sinks. So whatever air we have trapped in here does not leave at all. And because we put a lid on, it can't freely exchange with the outer atmosphere and the external environment of P2. So we know that whatever air is in here initially, when we put our lid on top, is going to be the same air no matter where our height falls to. So the amount of air we have trapped in this container is the same, meaning the moles of air is the same. And the fact that I use the word moles might clue you in. We're going to use PV is equal to nRT for this. So we know PV equals nRT. So the number of moles of gas, so N, I'll call it N air, is going to be equal to however much air we put in at the beginning, because we know most of those quantities. So PV divided by RT, so pressure initial times volume initial over RT. Those are constants. And since we know N air is going to be the same no matter how our internal situation changes volume and pressure-wise, because again, these two are constants, we're assuming constant temperature, and this is a definitional constant. We're going to assume, we know that no matter how pressure and volume change, the amount of air in there stays the same. So this is going to be equal to our pressure at any, our P1, our pressure anywhere whenever we move height, and I'm going to use capital V, I'm going to make it Roman again, because it'll be our volume at, again, any point in our H moving around a zone, and RT. And obviously we can look at this and pretty easily know we can cancel the RTs by just multiplying both sides by RT. And since the thing we're looking for is P1, let's kind of solve for P1. So P1 is going to be equal to, we just divide both sides by the Roman looking V. So we have pressure initial times volume initial over the current volume. So this, okay, now we're done, right? We've solved for P, we've solved for the differential equation. We needed V2, we solved for V2, but it needed P. So now we've solved for P1, right? So we can put a box on this and call it done, right? I figured out twice. This is the real one this time. This is real for sure. No, I faked you out again. But we're not done. And that's because PI and VI and V all still depend on height. So we don't know what the volume is at any certain time. We've related pressure at any time to a volume, but we don't know what that volume is. So this is the part where it gets really interesting, because our volume directly depends on height, as it's the thing that changes with height. This is the most direct causal link between changes in height and the whole pressure volume flow system we have described here. So what is our initial volume, and what is our, because our initial pressure, as we discussed earlier, is just P2. It's the external pressure, so we can just swap those out. What is our initial volume? Well, again, we talked about for volume here, we knew it was the area of the cylinder and the change in the height. Well, that was for the derivative, of course. But so it's the area and the height. So we look and we say that, well, we're talking about the volume of our air specifically. So if we have our whole container full of, air and gas, whatever volume is not taken up by fluid must be taken up by gas. And since we know the height of our fluid in this tank, and we know the area of the whole tank, we can simply call this the area of the cylinder multiplied by the height that isn't attributed to fluid, RH. So for the initial point, we know that that's going to be HI, so the difference is going to be the difference in height between the tank, capital H, and HI is the height that represents the initial volume multiplied by the area of the cylinder. And then the same thing is true for any random height, or not random, again, declining height here. The difference between the total height of the cylinder and the height of the fluid is going to be the new volume. So I can actually erase my little box around this because we're not done here yet. Come over here, blow the chalk just out of the way, and we can write that P1 is equal to, I'll just write equal to here, because I said P2, again, is something we know, it's our constant, it's our external. VI is going to be equal to the area of our cylinder multiplied by the height that represents the initial volume of air. So I'm going to use brackets here and do capital H minus HI. HI, again, is a constant. So we have that. And then on the bottom, the volume at any non-initial height, essentially, is also going to be the area of our cylinder multiplied by the total height of our cylindrical tank minus whatever height is currently occupied by water. So you can see that they're basically the same thing. It's just that this is a constant that we know we've been given, and this is some variable height that again changes as everything else in our system changes. So obviously we can see that the areas of the cylinder cancel out, and finally P1 is equal to P2 times the ratio between the initial height, or the difference in fluid tank height at initially divided by the difference in fluid and tank height at some different height. This is a sloppy looking lower half of our fraction. So we rewrite it, minus h. And this is the kind of the final segment, because we've finally reached we've reached derivational bedrock here. We've gotten, our dH/dt in terms of V2, we've gotten V2 in terms of Pi and H. Now we've gotten Pi just in terms of P2, which is a constant, capital H, which is a constant, and HI, which is a constant. So we're going to throw this all together into one thing as V2, because the way I'm going to code it up in Python is we're just going to define V2 since it's in a square root, so we can take care of that easily, because part of our Python work is going to be figuring out when our velocity hits 0 and the volume in our tank becomes steady state. So it'd be best to not write the whole thing out as one dH/dt equation. It's better to kind of define V2 separately. So I'm just going to draw my little arrow plugging here into this guy. And then when I substitute that in, we can write that the velocity of our fluid leaving is going to be equal to the square root, I'll make sure to write it really big so I have plenty of room, of 2 GH plus 2 multiplied by something's beeping, I don't know what that is. It's hopefully not my phone and I'm still recording. Multiplied by, well, P1 is P2, so I can factor a P2 out, and I can factor a row out from both of these. So I can have 2, I'll put this on top, 2, oh, I wanted to write 2 P2 over rho, and then all that's going to be left is the P1, which is the difference in the heights, minus, well, we already pulled that out of there, so that's going to be parentheses H minus H initial over H minus H, subtracted from 1, because we're pulling P2 and rho out of this right here, and P2 and rho out of this right here. So this is going to be our final equation for the velocity of our fluid leaving our tank. So when we go into Python, we're going to define V2, we're going to define our differential equation, and then we're going to use solve IVP to numerically solve them and get a function that returns height as a function of time. So we're going to step into Python right now. Look at my fingers, you're getting very sleepy, and here we go.
Hello, and welcome into Python. Now that we're here, we're going to take everything we just did on the blackboard and make it usable with a code to spit out actual numbers. As with Python, as we usually do. We're going to start by importing the basics. We're going to start by importing numpy as np. It already knows what I want. Then we're going to, in order to graph everything, obviously we're going to need to import plotly from plotly. So from plotly dot subplots. We're going to import make underscore subplots right there. And then finally, we're going to need to, again, we just solved for a differential equation on that whiteboard. So what we're going to have to do is we're going to have to take that differential equation and get an equation out of it that represents that derivative. So how do we do that? Well, we're going to use scipy, SCI, pi, dot integrate, and we're going to use their function called solve underscore IVP. So what that's going to do is it's going to allow us to write the right-hand side of the equation, what we solved for with V2, the area of the cylinder and the area of the hole, and using that, we'll be able to find a function for the height over time, obviously that follows that derivative, that definitional derivative that we just came up with. So the first thing we're going to do is we're just going to define a bunch of the constants we were given, because again, before we said we knew a bunch of values, but obviously now Carlos has given us the numbers he'd like us to plug in so that we get a graph that is standardized and has an actual value. So we're going to start by doing the maximum height of the tank, which is going to be equal to 1 meter. I'm going to put the little units next to it, so that's capital H. The cross-sectional area of our container is going to be equal to, again, 1 meter squared, so 1 m to the power of 2. I don't like doing m2, it makes me confused. The next thing we're going to get is the initial height value, which also is the highest height value since it's draining, and that's going to be equal to 0.9 meters. The next thing we're given is the pressure above the liquid inside of the tank, so P2 as we called it, but that we said was equal to the pressure outside the container, P external. So I'm just going to call it P external, and that's going to be equal to 101.325. That's going to be in pascals. I'm going to go and put periods after both of these ones, so that way we remember that we indicate to Python that yes, this can be a float, it's not locked as an integer. And then the last number that he's written down in our homework is going to be the size of the hole, the area of the hole specifically. So a hole is going to be equal to 0.001. That's going to be in meters squared. But that's not all the values we're going to need. Obviously, since we're dealing with gravity as the force pulling down, we're going to have g. So g is going to be equal to 9.81. Got those numbers mixed up in my head. And that's going to be in meters per second squared. And the final number we need to know, which is always very important and rhymes with no, is rho. And that's just, in metric units, 1e to the 3, and that's in kilograms per meter. Again, rho does represent the density of our fluid. And then I'm just going to put up here, along with all of these, the duration we want our simulation to last. So I'm just going to throw a number up here for t end, and I'm just going to say that's going to be 10. So that one's not getting a unit because it's just 10. It's 10 units of time, which I guess could be theoretically seconds. Stop doing that, 10 period. Okay, so those are all of the units we're going to need. So now we're going to actually write up the right-hand rule. Or not the right-hand rule, that's for electromagnetism and for magnetic force. We're going to write up the right-hand side of our differential equation. dH dt is going to be equal to what? So I'm going to pull up right on the screen. It's going to fade up nice and calmly for you guys. We're going to define a new function, which I'm going to just call RHS, that stands for right-hand side. And it's going to take in 2 arguments. So the first thing is going to be the time, right? Because obviously we need to know how the height changes over time. And the other thing we're going to need is, because again, this solves this differential equation problem iteratively by continually plugging in different height values over and over and over again in order to plot it and then figure out what the equation looks like. But because it does it iteratively, and this theoretically could be used to solve functions with multiple inputs and outputs, we need to input it as a vector. So we're going to make sure that we have a vector that represents our height value. So the first thing we're going to do is we're just going to instantly unpack that. So our actual height value, since we only have 1, is going to be equal to 0. Now the next thing we're going to do is we're going to define V2, since that was a very special derivation for us and hit me close to home. And it will come up in this kind of the later portion of our assignment. We're going to write that down. So V2, as the board says, making sure that fades in right about now. It's just going to be the square root np.sqrt. Make sure I spell that correctly. The square root, and inside that square root we have the 2 that I'm just going to pull out to multiply by. So 2 multiplied by, and that's going to be G times H plus, and then on the other hand with the 2 gone, it's just going to be P external divided by rho, and that is going to be multiplied by, I'm going to make sure to wrap Px times rho in parentheses just in case. Well, what's multiplying, what is P external divided by rho multiplying by? Well, that's going to be the ratio of the height minus the height initial from the height minus the current height we're looking at minus all minus 1. That's going to be a bit of a doozy, so I'm going to do the minus 1 dot over here. That's the minus 1. So this is where the fraction's going to go. So it's going to be h minus hi divided by parentheses h minus h. And this whole division thing, again, we want it to, this should be divided before the subtraction takes place, so I don't think I need to indicate anything there. So that's going to be our V2, and of course that's not the whole of the equation right there. We also need to know, the actual whole right hand, because that's just V2. So the actual right hand, which is what we're going to return, is going to be, well, it's going to be negative the area of the hole over the area of the cylinder, so the ratio between the two hole areas, multiplied by V2. So I'm going to just put this in parentheses, negative a hole divided by AC for cylinder, multiplied by V2. So you might think, okay, Ethan, we're done. You can save it, but we can't, because remember, we're putting in a vector and we're taking out a vector. So if we're putting in a vector of h, and even if it's just one value, that's h, we need to make sure what we're returning is also a vector. So now that we've done that, now our right-hand side is complete. And of course, knowing that you needed to do that is an important part of knowing what the right-hand rule is. Not the right-hand rule, again, what solve IVP does with the right-hand side. So what we're going to do is we're going to do solve underscore IVP. And what does solve IVP take? Well, first it takes a function, so our function is going to be the right-hand side. What next? Well, we're going to take the p-span. This is going to be some kind of, this is going to be a tuple of times that we're going to be looking at. So we're going to look at, obviously, the 0. We're going to start at 0, and we're going to go until t max, or t end. That's why we wrote it up there. So we want to, that's the duration over which we're going to be looking at. And obviously we can always adjust t end up above if we need to. Next we're going to need y0, so what's the starting guess? The easiest starting guess is just going to be the high point, hi, because that's where it starts. So we know that definitely isn't kind of like outside of reason, like something above 1 would kind of be outside of reason since that's the maximum height of the tank. Couldn't be bigger than that, and if it were started out at 0, it would be empty, so it wouldn't really go anywhere. And then we're going to need to know the method. So the method we're going to use is going to be Carlos's favorite, R-A-D-A-U, Rado. Yes, Rado. And obviously, if we want to actually get a function out, we have to set dense output to be true. So that's going to be true. And that's all we're going to do right now. So because we have dense output true, it will obviously only be, it will only know the value for the values it iterates over, correct? Like it will keep doing this, and it will keep iterating, but it only has, a finite number. But once it's done, if you have dense output set to true, it will give us, well, you'll see, it will give us a, this was an expected error, but it interrupted me thinking. It will be able to give us a part of what it will return will contain a function that will actually be a solution for that differential equation over all points of time. So anyway, back to what we've gotten. We have an invalid value accounted in square root. Now, just to avoid this temporarily, I'm going to chalk this down to 1. I have to redefine this, 1. And it does work. It reached the end of the integration interval. Notice it didn't say it converged at all. It just said it reached the end of the interval. And you can see right here, there's the sol right here. That is the function that tells us what we're, like this is the actual function right here that we can take, we can plug in any range of t's and get an answer out. But you'll notice that when it was short, t end, it works fine, but when I set it back up to 10, and we run into an error, an invalid value in the square root. Well, we know that the domain of square root, you can't put a negative number in there because nothing squared gives a negative number unless you're talking about imaginary numbers, but obviously you can't have an imaginary height of water in your tank. It has to be a real number. So how do we go about fixing this? Well, the band-aid on the wound is going to be just putting an absolute value in there. So if we put an absolute value in there, there's no way we can get a negative number. And the reason we're getting a negative number is because G times H, I want to move that around, is some positive number, right? Because G is positive and H is positive. But this right here is not necessarily, because this right here is not necessarily, because we have a ratio subtracting, and we're subtracting 1 from it. So if this ratio is smaller than 1, we're going to get a negative number here, which multiplied by this is going to be a bigger negative number, which if it's possible to overwhelm, if that negative number is more negative than g times h is positive, we'll get a negative number here times 2, and that inside of a square root won't work, because for obvious reasons you can't have a negative in the square root. If we put an absolute value in there, we see that it does work this time around. So what we're going to plot what this looks like, and we're going to see what this does as a result of doing the absolute value. So to plot it, the first thing we're going to do is we're going to need to have a range over which we're looking. So we're going to make a new thing called tplot, and that's just going to be np.linspace from 0, to tend. And we're going to do, say, 101 slices right there in that array. And then we're going to need yplot, which is going to be, we're going to have to define this. So right here we said we have the sol, so we're going to do say dot sol here to get that actual part of our return. It's a dictionary, or it's not a dictionary, but that's the attribute we want. It gave us an object, that's the attribute. And so we're going to call this sol, just because I'm uncreative today. So yplot is going to be equal to sol taking in tplot. So again, it's going to plug every single value of tplot into the function sol, and will obviously give us an array that's tplot long of all of the outputs of that height function that it derived for us by running the solve IVP function. And then we're just going to graph it. So we're going to call fig1 is equal to make underscore subplots as a function. Nope, not like that. There we go. And then we're going to do fig1.add scatter x equal to tplot, y equal to yplot, and then mode is equal to lines. And then because I'm fancy and bougie, we're going to do fig1.update layout. Parentheses. We're going to have template equal to plotly underscore dark. If we plot this, we didn't get anything. Is this because something's going wrong funky with so yplot? Let me look at yplot here for a second. Okay, so it's an array of just arrays, and I'm trying to remember the reason why it's doing that, but I don't. So it's the only, I think maybe it's because, again, it expects to get an array full of arrays because, again, solution can work for multiple values. Like, again, you could be solving for multiple things changing at the same time. So if I do yplot 0, then it will just get rid of that extra bracket right there in the array, and all will be solved. So I'm just going to put a 0 here, get rid of this extra little thingy, and now it should work. There we go. And you can see right here, it's going normally as we'd expect, and then it kind of bottoms out here. It gets very flat, and then it starts decreasing again. And that's really odd behavior, because what we expect is that eventually it would get to a point where the velocity at 2 becomes 0, and it would just stagnate, because once the velocity is 0, no more water is flowing out, and it would just stop there. And this right here, where it kind of continues again, is thanks to our absolute value that we plugged in. So this, right here, this is not what it should look like. This definitely, again, as I said before, that absolute value is just a boo-boo to get it stopped from erroring. We have to figure out why it's doing this. But we actually know why, and it's part of what we're required to do for this homework assignment, which is to use the T event system. If you look here, put a comma space, you see right here, there's something called, right here, events any. So what this is that it provides a way to prematurely stop the solve IVP function from running if certain conditions are met. So instead of the default event, I guess you could say, is that when you reach T end, stop. That's a pretty obvious default condition. What we're going to do is we're going to make our own condition that will tell it when to stop. So I'm just going to call events equal to, and then I'm just going to put enter. Actually, I'm going to put events on its own line so we can see. So events is equal to blank. And I'll leave a space right there. So I add a big red angry line right there to tell me that I forgot something if I forget, which I won't. So what event are we going to do? Well, we want to stop our solve IVP from running when we reach steady state. So when would that be? Well, that would be when the height level isn't changing. And when would that be? Well, that would be when the velocity is 0. Because once velocity is 0, obviously that multiplied by the ratio between a whole and ac is 0, and that's when our derivative is 0. So when our derivative is 0, that means v2 must be 0. So I'm just going to put comments up here that says equal to 0 when v2 is equal to 0. And when is v2 equal to 0? Well, that's when this right here, obviously, that's just, that's accepting the square root, because obviously the square root of 0 is 0, and we're going to ignore the absolute value. When this right here is equal to 0, that's when our velocity becomes 0. So that's also more precisely, you can get rid of the 2 and also say when gh is equal to r ext divided by rho times the ratio h mess minus 1. But we don't have to do that. We don't have to do that multiplication. So I'm just going to make sure I grab the right parentheses right here. Yep. Grab this right here. I'm just going to copy it, and we're going to make our new event. So we're going to define, we're just going to call it v2 is 0. So what is this function going to take in? Well, it's going to take in our t, and it's going to take in a vector as well. Because again, nothing's really changed in particular from our previous one. So h is again going to be equal to vec 0, because we're only inputting one independent variable, one input and output to again check against. And we're going to return something. So what are we going to return? Well, I'm just going to paste this in here for now because we know that this is one of the things we're going to have to calculate, because we got to know what v2 is in order to figure out if v2 is 0. So how the event system works is, when does it trigger, right? So I said we can set a custom event. Well, the event is quote-unquote triggered when the function you set as the event reaches 0. So in our case, since we care about when v2 equals 0, that's very easy. We can just return what v2 is, and when v2 is 0, our function will be 0, and so our thing would stop. But for example, if we wanted to stop it when our v2 was like 30, we would return this minus 30, and when that reached 0, then we'd be good. I also have to put this in an array, because again, we're inputting an array and we're outputting an array. So we have to make sure we define that. I'm going to redefine this and redefine this, and this should be our v2 is equal to 0, termination event, if I remember how the events work correctly. I feel like there's a fly landing on my neck, but the camera behind me can probably evidence there is not. So events, it's going to be equal to v2 is 0, and we're going to see if this works. So no errors. We got an error. Must be a real number, not a list. I do not know what that means. Must be a real number, not list. Let me double check how events are returned. We do a solve underscore IVP question mark. Tell me. All right, take me to. This thing looks really funky because it wraps around. There we go. Doing that helps a lot. Events. Callable or list of callables optional. Events to track. If none, default. Each event occurs at the 0 of a continuous function of time and state. Event t, y, and return a float. Okay, so we don't want it to return an array. We want it to just return a float. There we go. So that's that fixed, hopefully. I'll keep that around, but I think we'll need it. There we go. So it ran. It didn't give me the pop-up again because I already have it set to get the dot sol and do that. So we're going to run this, and we're going to see what this plots. So actually, we're going to run this again before we plot it, just to double check, because it would feel a little silly if it, it's converged. Oh, that's not what I want to delete. I want to delete all of this. So run u. Solver successfully reached the end of the integration interval. Success is true. I'm assuming that means that it reached 0. So that is t events. Yes, so t events right here. So at 4.56135863, we hit an event and it stopped. So I think that's good. I think that means it did in fact hit an event. So it says reach the end of the integration interval. It didn't say like iteration interval. So I think that means it did its job. So I'll undo that, put those back, and we'll graph it, and hopefully it will just be a nice gentle curve until right here, and then it will stop. So we'll see what that looks like right now. It did not do that. Okay. Why did it not do that? It said there was a t event. Did it not stop when solve underscore IVP, question mark, enter. Okay, check events. Terminal. Okay. We want to terminate the integration if this event occurs. Okay, so how do we where do we want terminal to be equal to true. So I think we have to just set that up here. Terminal is equal to any function in type Python. Okay, that's how you do it. So we want to make sure that this is terminal. So we're going to say v2 is 0. That's our function. So we're going to do function dot terminal is equal to true. So that's saying that, hey, when this function reaches 0, we want you to stop integration. So it did. I was right. It did in fact see that. Get rid of sol and get rid of. I just did it again. Why was it doing that? I want you to just delete that. On this, the termination event occurred. Okay, so there we go. So before, because as I said before, it did see a t event. Like before, if you looked previously, it would be empty. Now it's set at 4.56135863. There was an event. And now we can be certain that it did stop because it says it stopped. So I'm going to put that back again, run this. And now if I plot it, there we go. Not exactly the shape I was expecting. It was normally more of a slow, gentle curve down. Is it possible because the termination event works perfectly fine. Is it possible if I do it as down, is it? No, but not. Yeah, why is it going like that? This is definitely not supposed to. And we saw before, there's just a graph that stopped. Maybe it's going to t end. Okay, let's look at this again. Termination event. We want you to go until t events. So we're going to, here's what we're going to do. We're going to call this sol. So this. And what we're going to do is we're going to instead of to t end, we're going to make a plot from to sol dot t underscore events. And then since that's an array, we're going to want to do 0. And then from here, we're going to want to do the same thing, like that. ODE. I have to run this again, and then call u. Sol dot sol of t plot 0. Oh, come on. Oh, I think I have to do it like this. And then, yep, okay, now 0 here. There we go. Okay. Bit funky. It was because we were overplotting t, and so it would just, that function went haywire. But here we go. Now we have our nice calm plot. It starts at 0.9, it starts going down, and then it tapers off before leveling out and it stops. So this is our plot. This is what happens. There was a bit of kerfuffle in the beginning because we had to make sure, we had to redefine how sol was. Instead of just getting the solution, we also had to get the events, and then obviously that was double layered in an array, so we had to fish that out as a. The reason it was giving me a broadcast error was because I didn't have that second 0. So what it was doing was it was feeding it from 0 to an array, and of course that I think made just a bajillion arrays of stuff, which is bad. And obviously yplot didn't like that. But you know, when we took care of it, and everything worked out just fine. So we have our plot right here. It's very calm, cool, and collected, gradual. It does come down to a stop, and it does stop when our velocity became 0. So I thank you for tuning in today. I wish you the best evening. And I hope you really enjoyed what we worked here today. So thank you for tuning in, and bye-bye.